Okay, now we're going to do test revision on statistics. The first question is on the effect of a drug on the weights of rats. The first group is the rats taking the drug for weight reduction, and the second group, they're not on any drugs, so they're called the control group. We have to display the data in all the different graphical representations and data representations that we've learnt in class. The proviso being that we should have between 5 and 7 categories. The reason we want between 5 and 7 categories is because then it will actually display whether it's a normal distribution or not. If you have too many categories, the columns won't be high enough to actually give a normal shape to the histogram. So to work out what the class interval is, we just get our maximum. So let's take group 2 for example. So the maximum value, we've got one there, so around about 150. The minimum value is like around about, say, 90. So we're going from 90 up to 150, a span of 60. Now if we want to have about 6 categories, then the class intervals would be 10. So that's a nice even number to use, and that's what we'll be doing here. So in the graphics calculator, you should put all the values into list 1 and list 2, and then do second stat plot and produce the histogram. I've done it here. We can see that the control group is this one. It looks roughly like a normal distribution, but we could say it's positively skewed, because we could say the shape's like this with a big tail to the right. And so it says the histograms highlight that the rat's weights are normally distributed, but I've got here or slightly positively skewed, but it's definitely not negatively skewed for both groups. However, the group on drugs have weights distributed about a lower mean. Or rather, that should be lower median, because the middle value here is the median. So you can see that I've done a side-by-side box plot, so keeping the categories lined up. So we can actually see that the median here is occurring around this value, whereas the median with this one is occurring around this value. Okay, and if we're talking normal distribution, we could use the word mean, because the mean is actually in the center of a normal distribution. So clearly this is showing that when you place the rats on the drugs, that this shape heads towards the left to look like that blue graph there. The next thing we can display is box plots. Likewise, you go second stat plot in the graphics calculator, choose the box plot, and we can see straight away that the rats on drugs is the blue one. That's shifted more to the left. The control group is a little bit higher, so placing a control group on drugs would actually reduce their weight. We can see that the median here, this solid line, is lower for the weight, the drug group, which is on weight reduction. And we can also see that they're also showing normal distribution, because the line's in the middle of this inside box, showing that there's equal spreads, because there's 50% in that box, 50% in that, sorry, we can start again. There's 25% in the tail, 25% in the box, so 50% in that whole region. There's 25% there, 25% there, so there's 50% in that region. If it was positively skewed, you'd expect this line to be there, because a lot more of the data, like 25% is spread over a small region, whereas 25% is spread over a larger region, and that would be corresponding to a graph looking like that. but in this case they're both symmetrical. So that's what this says. It says it highlights the normal distributions, but also the drug group is distributed about a lower median, but also highlights that the spread of the middle 50% of the data is slightly larger for the group on drugs. So this spread here is slightly bigger than this spread here. If it was a lot bigger, like if it extended over to there, then the effect of moving this median back is kind of outweighed by the increase in inconsistency or variability of the data. But because the spread isn't that much different, then we can see the median has been significantly reduced. You can do it on pie charts as well. I've done this on Excel. You'd have to do it manually in the test because you don't have Excel there, so you have to check your book to see how you do that. But first of all, you have to express it as a percentage. That's what this column is, and then you times that column by 360 to get the angle. These are all the angles here. Now to get the percentage, that means you've got to do 1 divided by 19, 3 divided by 19, you divide by the total. And all that this highlights pretty much is the modal class, the biggest class. So here it's the grey one, which is the 90 to 100 category, and that's running at 26%, as stated there in the table. Whereas if you compare it to the rats not on drugs, their biggest value is this, looks like this blue one here, which is the 110 to 120 group, and that one's running at 29%. So clearly it's saying that the rats on drugs have a lower weight for their modal class compared to the rats not on drugs. So clearly the more rats are being reduced in weight there. And that's what it says there. The pie charts do not give us an indication of distribution, only modal class, with the rats on drugs having a high modal class of 110 to 120 compared to the rats on drugs with modal class 90 to 100. We can also do data summaries, mean, mode, median of each group. So there's a summary which you'd get from the 1var stats in the graphics calculator. We can see that when the rats are on drugs, that the mean goes down, the mode goes down, and the median goes down. So clearly they're all showing the same effect. The standard deviation you can also get from 1var stats on the calculator. And you can see that the rats on drugs is slightly bigger. The spread of data is 15, whereas the control group is only 14. But that's not much of a difference. Now we need to interpret the meaning of the standard deviation. So rats on drugs have a spread of data, a high spread of data, as 68% of the weights lie between plus or minus 1 standard deviation, which in this case is plus or minus 15. Okay, so it's the 68, 95, 99 rule. If you have your mean here in the middle and you add on 1 standard deviation and you take off 1 standard deviation, then 68% of your data lies in that region. Now if you take off 15 and you add on 15 to the mean, which is 105, you'll get these two values here. So 68% lie between those two regions. All right. Whereas if you look at the one on drugs, not on drugs, then you'd have to take off 14 and add on 14 to the mean, 113, and that would be 98.4 and 127.6. That would actually be 68% of the data between those two. Okay, so the spread of data for the rats on drugs is a lot larger because it's going from 89 to 120, whereas this one it's going from 98 to 127. It's very similar. The range of that one is only 29.2 because it's double 14.6, whereas the span of the other one is 30.6 because that's double the 15.3. Because it's one standard deviation is that amount, but we're talking about the span for 68%, so we're 2 standard deviations across. That's for 68% of the data. For 95% it would be plus or minus 2 standard deviations, and for 99.7% it would be plus or minus 3 standard deviations. It says, however, the difference is negligible compared to the overall reduction in weight seen in the mean, mode and median. So 30.6 compared to 20 to 29 is not much of a change in the spread of data. Okay, so yeah, you can see that getting the statistics and the graphs is one thing, but analysing with these words is another. And so you've got to be good at analysing the meaning of this data and all these representations. Okay, question 2. We've got temperatures, and we've got the first 7 days, and we have to work out what the next day has to be, the temperature, in order to get a mean of 6. Well, the sum of all the numbers divided by the number of the numbers is the mean, because the mean is equal to the sum of the numbers divided by the number of numbers. So if we put all that in there, and the last number being our unknown, which is x, our eighth day, and divide by 8, then that all has to equal 6. Now if we add up those numbers, it's 25, we've got plus x, we times by 8 over to the other side, so that's 48, subtract 25, so x, our 8th day value, has to be 23 degrees. If we want a median of 3, we rank order the numbers, so 1, 2, 3, 3, 4, 4, 8. Now we can either place our unknown number to the right or our unknown number to the left. If we place it to the right, then the middle value is between 3 and 4, and we won't get a median of 3. So clearly that's not the place to put it. If we put it on the left, we'll get the median occurring between 3 and 3, which is 3, so that works. So basically we could place x anywhere in this region here. So it can be, as long as it's less than or equal to 3, all the numbers are going to give a median of 3. The next one, we've got to get a standard deviation of 2. So we write the formula down with the summation sign, sigma, and we place in for n 8, there's 8 values, 8 take 1 is 7, and we square both sides, so 2 becomes 4 and we lose the square root. Then we times both sides by 7, so we get 28, 7 4 is 28, and so we have this value, the summation sign, equaling 28. Now the x bar in that bracket is defined in part A, and that's 25 plus x on 8, which we did just a short while ago in part A. And the xi refers to all the individual numbers. So the first number is 1, so we have 1 take the mean, and then the next number is 4, so we have 4 take the mean, and then we repeat it for all the numbers, so that's dot dot dot, you fill in all the rest. And then the last number is x, the unknown, so it's the unknown take the mean. They're all squared and they're all summed because of that sigma sign, and that equals 28. Now it does say in the question, write an expression in terms of x only, so that's purely in terms of x. We finish the question. You could solve x if you put all this in the graphics calculator, but the question isn't asking for that. What you could do is put all of that into the y1, and you put in for y2 28, and you intersect the two lines, and that'll give you what the x value is. Next one's box plot. The shape of the distribution is positively skewed because this line here is not in the middle of the box, it's slightly to the left, so it's a positively skewed graph. What's the interquartile range? It's the upper quartile take the lower quartile, so we get 8. The median is 5, that's this middle value here. Is 18 an outlier? We have to get the outlier regions, and the outlier region is the mean plus or minus 1.5 times the IQR. The mean is given in the question as 6, so 6 plus or minus 1.5 times 8, you get minus 6 and 18. So up here, the outlier regions is -6 and 18. So anything, these values here are considered outliers, but the actual number 18 is within that region, so it's not an outlier. Would you expect the standard deviation to be bigger or smaller than 2? Now the IQR contains 50% of the data. This is the IQR, this box here. 50% of the data is in there, ranging between 2 and 10. It's like between 2 and 10. Now standard deviation, 68% of the data lies between plus and minus 1 standard deviation. So if S equals 2, then plus or minus 1 standard deviation will be your X bar plus 2 and X bar minus 2. So that's 6 plus 2 and 6 minus 2. So we're between 4 and 8. Now 68% would have to lie between there. But that doesn't make sense, because if 50% is between 2 and 10, how can you have 68% between 4 and 8? Because 4 and 8 is a smaller region than 2 and 10. So clearly then S has to be greater than 2 to make this make sense. This one here is about producing margarine containers. So this company produces the same mean as this one, but the standard deviations are different. So this company here is more consistent in producing cans centered around this 279 mean, whereas this one's more varied. Okay, comment on which manufacturer is better at making margarine containers. So company A is more consistent. However, if you look at what's stamped on it, it's 275. Company B is going to have a lot more which are closer to the stamped value of 275. So you could go either way as long as you justify it. Using the 68, 95, 99 rule, determine what proportion from company A will lie between these two values here. Now this is two standard deviations. 279 is 4 away from 275. Now 4 is 2 lots of the standard deviation of 2. So 2 standard deviations you must have 95%. So you don't have to use your normal CDF, you can just use that using the 68, 90, 95, 99 rule. Now, between what two weights for company B would give the same proportion, so we want to have 95% also. To get 95%, we need to be 2 standard deviations, but the standard deviation of company B is 4, so 2 lots of those standard deviations are 8, so we have to do plus or minus 8. So we do plus or minus 8, we're going to get these two values here, which will contain 95%. Part D, if by law cans below 275 were considered to be too light and required to be rejected from the production line, how many would be rejected if it makes 1,000 cans a day? Now for company A, less than 275, there are 2.5%. To get that value you could just use normal CDF and in the graphics calculator, so that means 2.5% less than that stamped amount are going to be rejected. Now 2.5% of 1,000 is 25, so it's 2.5 divided by 100 times 1,000, so 25 cans are rejected every day. Whereas if you do it for B, if you do the normal CDF here using the company's B standard deviation, you'll get 16%, so 16 cans are rejected per day. Now remember, when you do normal CDF, you've got to do normal CDF, you do your lower, put in your lower value, which is minus E99, the upper value is 275, and you follow it by the mean, which is 279, and the standard deviation. If you're doing company A, it's 2. If you're doing company B, it's 4. Part A, the manager of Company A wanted to change the law so that 1% were rejected. So to reject 1%, that's this rejection region, we're going to do the inverse norm with the probability and the mean and the standard deviation, and you'll get the 274 is the cutoff. So if he wanted to change the law, he would have to move it down to 274 grams, were to be considered too light. How many cans will company A and B need to reject every day if this new law is passed? So we now repeat it with this 274 as the maximum value. So normal CDF minus E99 and as the lower, and 274 as the upper. If we do that, we'll get 1% for the A, company A, which is 10 cans per day, and for B we will get 10%, 10.6%, so that's 106 cans per day rejected. Okay, so a vet is looking at normal hair growth during the winter season. If the hair growth is 1 centimetre a month, it has less than 1 centimetre a month, then it has problems with malnutrition, and that occurs for 4% of the dogs. If it grows too quick, this is for 10%, they grow more than 5 centimetres a month, and that can have problems. So these are considered the bad rejection regions here. Now what would you expect the mean hair growth to be? We want to know what mu, this mean hair growth, is. So we do, first of all, inverse norm with the 1, inverse norm of 0.0401, and you get that for the Z value. You do inverse norm with the 5 and you get 1.28, so they're the Z scores. And then you apply this Z formula into these two Z values to get simultaneous equations. So we have, using the Z1, that corresponds to the raw score of 1. So that's the Z score, that's the raw score. Over here we have the oh no, this, start again. Over here, over here we have the 5. That's the Z score for the 5, and that's the raw score for the 5. Now when you multiply both sides by sigma, that will convert into this one, and that will convert into this one. So these are the two simultaneous equations. We subtract those two, because if you want to eliminate mu, you have to be minus mu minus minus mu, which is minus mu plus mu, which is 0. So you do that value, take that value, take that value, and you'll get the minus 3 equals minus 4, and so you divide both sides by minus 3.03, and so sigma is 1.32. Plug that back into equation 2, and you'll then get the mean as 3.3. Question 6, relay race of 4 is to be selected from 8 male, 4 female. How many different teams can be selected if there's no restrictions and order doesn't matter? That's C412, selecting 4 people from the total of 12. Put that in the calculator, you get 495 different combinations of teams of 4. And when it says order doesn't matter, that means like if you had, say, John, Sam, Bill and Brittany, it doesn't matter about the order. It could, if Brittany's was selected first, it's still considered the same pattern. So it says here order doesn't matter. That's what combinations are about. Combinations are, that would be different to John, Sam, Bill and Jake. They are a different combination. But this one here, if you swapped BSB, they're considered the same combinations. They're different permutations, but the same combinations. Okay, the next one now asks for how many permutations, because the order matters now. Now do the permutations. There's 12 ways of selecting the first member, and there's 11 ways of selecting the second member, because you've actually chosen one, and then 10 and then 9. Multiply them, there's 11,000. So if order matters, there's 11,000 different teams you could have. If order doesn't matter, there's 495 different teams. If there must be 2 runners of each sex, so that means you have to have a male, male, female, female, not necessarily in that order. Then you've got to select the males. You've got to get 2 males from the 8 males, as well as 2 females from the 4 females. If you multiply them, there's 168 different combinations. If there must be 1 rider of each sex in any order, you can have a 1 male, 3 male, 1 male, 3 female, 2 males, 2 females, or 3 males, 1 female. There's no other combinations. Notice the ors is really plus in maths, and in between it's 1 male and 3 females. These are times. So it's times with these, and it's pluses between the different options. If you do all that, you get 424 combinations. Part E, what's the probability of selecting a team of 4 where there are 2 runners of each sex? So this is how many teams you can have. This is the probability of teams. Now probability is how many out of the total. Now we've just selected, because this is about the 2 runners, so that's actually talking about this one here. How many in this one? There are 168 of 2 runners being of each sex. So it's 168 divided by the total, and the total is what we had up the top here, 495. So it's 168 divided by 495, which is 33% chance of selecting something like this one here, where 2 runners of each sex are in the team. Now question 7, a coin has on one side a male and on the other side a female. Now I've added this one as an extension because it links this counting combination theory with probabilities. So if you were to flip the coin 4 times, you have to draw a tree diagram. Now in the first toss you could get a male or a female. In the second toss you could get a male or a female after throwing the male first, or after throwing the female you can get a male and a female, etc. And this one here is the 3rd toss, and this one here is the 4th toss. So you can see that this represents all the different combinations that you can have in throwing a coin, in this case the coin with a male and a female on either side. So for example, if you wanted to get the 4 males in a row, like 4 heads in a row, then it represents this branch along here. There's only one option there, so the probability of getting that is 1 out of 16, because there are 16 total combinations there. Okay, now it says illustrate in the diagram the outcomes for obtaining 2 males. So the 2 male options is this one, a male, male, female, female, so that's going along this branch, male, male, female, female. You could have male, female, male, female, so that's 2 males, 2 females. That's going along this branch, male, female, male, female, and likewise you can do these others. In all cases, you've got 2 males and 2 females. Now you can see, if you look, there's 1, 2, 3, 4, 5, 6, so there's 6 out of the total 16 possibilities. Part C, expand this bracket, male plus female to the 4th. That's like a binomial expansion where you start off with C04, then it's C14, C24, C34, C44. This is Pascal's triangle with the coefficients. You put the first one, the male, with the highest power, and then go down one. So it's M4, M3, M2, M1, and the female, you start off with 0 and go up to the top, so that's really F0, F1, F2, F3, F4. If you put that in the calculator, your coefficients would be 1, 4, 6, 4, 1. That's Pascal's triangle, followed by these terms. Now, what's the probability of obtaining 2 males in the 4 tosses? We could use the tree diagram above. We did that before, where there are 6 options. 1, 2, 3, 4, 5, 6 out of the total 16. So we could say that it is 6 out of 16, which is 37.5%. Or we could use the binomial theorem, which you've just done above there. The 2 males is actually sitting in here. So there's 2 males and 2 females. That is the C24, this one here, C24. Now the probability of getting a male is 1 in 2. The probability of getting a female is 1 in 2. So it is 1 in 2 squared, 1 in 2 squared. If you do all that, you get the same answer. So that thinks probability with binomial. Now what we can do is actually link it to the original question of the riders. You can see here in part E, what's the probability of obtaining 2 males in 4 tosses of the coin if the coin was biased such that throwing a male is twice as likely. The reason we're biasing it there is because we're trying to compare it to the original problem here, where we've got a relay and we've got 8 male and 4 female, and there's twice as many males as females. So clearly it's biased by double. Now, can we mimic that with the coin just by having the coin being biased so that it's twice as likely as throwing the heads, which is the males, than the females? Now, if we try and do that using the same thing, so C24, but instead of a half-half, we're going to use 2/3 third, we get 29.6. So we get a different value to this, which we'd expect. But 29.6, that doesn't match up with what we got back in question 6, because the probability that we worked out for a team of 4 with 2 runners of each sex was 33.9. 33.9% was here. We are getting 29.6. Now, so can this method be used? Well, clearly it can't, but we can actually fix it up. But first we answer it by saying using that method we can't, because the problem is that when we're tossing a coin, it's sort of like when we're replacing the coin every throw so that the probabilities remain fixed. When you're selecting riders, you're taking them out of the pool and the probabilities are changing all the time. But we can actually fix that up by using a tree diagram where we change the probabilities. So if you went through a process like this, where you can choose the riders or the runners in the particular order according to their probabilities. For example, let's say you chose the first rider to be a male. Well, you've got 8 and 12 chance of getting a male, because there are 12 total. There are 8 males and 4 females. You've got 8 and 12 chance. Let's say you want the second rider to be a male, then the probability of that happening is 7 out of 11, because you've chosen one, you're not replacing that one, so the pool of 12 is reduced to a pool of 11. You've also lost a male, so you've only got 7 to choose from. So 7 out of 11 is now the second male probability. If you are then to follow by a female, well, the pool is reduced from 11 down to 10, and you've still got the 4 females, so it's 4 out of 10. And if you choose another female, the pool's down to 9, and one female's being withdrawn into the selection, so now you're down to a possibility of 3 out of 9. Now, if you want to know the probability then of selecting that particular team, it's 8 on 12 times 7 on 11 times 4 on 10 times 3 on 9, because it's a male and a female and a female. That's the probability of getting that exact selection in that order there. But there are other ways of getting 2 males and 2 females. For example, you could have male, female, male, female. So you have to multiply them and add that on. And as we saw before, there's 6 different cases, 6 different paths of that. So if you use that process, here are the 6 possibilities for getting two males, 2 females. There's 1, 2, 3, 4, 5, 6. You multiply the probabilities, adding all the options, and you actually get exactly the same answer, 33.9%, which we got in 6E. Now that's extension, that one there. I wouldn't expect you to know that at this year level, but we'll be doing that next year, and it just answers the question rather than just finish off by saying, can this method be used, and saying no. Well, I was just showing that a tree diagram can actually answer the question, but you'd expect to stop here at a year 11 level.